So without further ado, I'm very excited to introduce Dr. Ali Bashashati. Dr. Bashashati is currently the Director of Artificial Intelligence Research in the Ovarian Cancer Research Program at BC Cancer, as well as a faculty member in the Department of Pathology and Laboratory Medicine and the School of Biomedical Engineering at UBC. Dr. Bashashati's research area lies at the interface between computational, engineering, and biomedical sciences. He is interested in developing machine learning algorithms to combine various sources of omics and imaging data, including digitized pathology slides, in the context of cancer. Dr. Bashashati runs BC Translational Digital Pathology AI program and works closely with clinicians and biologists from various health sites. Through AI, they intend to improve pathology efficiency, identify new biomarkers for treatment selection, and derive biological insights that can be studied in various disease models in the lab. Thank you for joining us today, and I'll pass the microphone over to you.
Thank you very much. It's such a pleasure to be here. So today I'm going to talk about basically the pathology AI program at UBC, and with the specific focus on gynecological cancers. So I will showcase some of the work that we have done so far, and then some of the vision and also where we're going from here. So just to start with, so these are histopathology images of different cancers on top, and also the 5 histotypes of ovarian cancer that were actually generated by AI. So I think these days everybody knows about ChatGPT and also DALL-E, that is basically equivalent of ChatGPT for images. But we did this work actually in 2020. So these technologies are not that new, so they've been out there. So, but the interesting thing is that these, when we showed these slides to pathologists, they were not able to tell the difference between real and synthetic or fake images. You may wonder where we can use it, and then is it just, just playing with algorithms and then just for the fun? So I think, for this purpose and for this specific application of generating synthetic images, we are basically trying to use these images to augment pathology, AI models, which I will talk about later on. And also we can use these models for data sharing between institutions. And, it could be a good educational resource that it can generate, rather than having a few slides that teach residents, we can use these images that can be actually generated on the fly. And, it can be used that for proficiency testing and also regulatory purposes, like when you have these algorithms, hopefully down the road that they'll be part of the healthcare system, how you're going to actually stress test these models to make sure they're actually doing a good job as we go forward. But anyways, coming back, so this was just a teaser, and then, so I'm going to start with a bit of a history of this program, then highlight I would say 3 applications. One is the synthetic images that I briefly talked about, and also ovarian cancer type classification and endometrial cancer subtype refinement, and also we'll have some general concluding remarks. So a bit of history about the program. So, molecular, from 2007, 8-ish, when next-gen sequencing came in. So a lot of people started basically sequencing different cancers. Okay, and that includes different gynecological cancers. And these studies have basically come up with different subtyping of different cancers, that some of them actually have some sort of clinical implications. And as an example, wanted to highlight this study on top left. Let me turn on the laser. Okay, yes. In 2017, that we came up with some sort of genomic alteration signature based on whole genome sequencing data that we're able to stratify high-grade serous ovarian cancer cases into basically 2 subtypes with different outcomes. So I'll come back to this and why this is sort of important. So the question is, let's say most of these discoveries that were done on obviously next-gen sequencing, but most of them were done actually fresh frozen samples. And then if you want to take them to clinic, that becomes a big problem because in the clinic you have like formalin-fixed tissue material. So obviously translating all the things that we found in frozen samples is not easy in formalin-fixed material. So that was basically motivation that, okay, how can we actually make this easier? And in the meantime, so, there has been, again, lots of hype about like using artificial intelligence, AI in medical imaging. And examples are like, people have shown like this is from like a few years ago, that you can actually use these models to identify lymph node mets, like, in breast cancer. And it does actually much better than like pathologists. Not that they're better, it's just in the time limited environment that if you have like, let's say a minute to review a slide, which one would be actually better? Obviously, AI is a machine that, if you have a lot of computation behind the scene, that can be human. Okay. So that was the study on basically this one that was published in JAMA. And then there's been, again, lots of papers that have come out that link histopathology, even like some sort of genomic markers. So that was the motivation. And then for us to study this program, and so I want to pause here. And then this is like 18, 19. And then I was talking to Dr. Blake Jelks at the time, and about different projects. And then we were talking about obviously like digital pathology, AI, and then also the discovery that I mentioned about like high-grade serous and stratification. And he told me that at the time, so that was actually like the initiation of this program, that how about actually we try to see if we can build models that we can identify these subtypes from histopathology images. So, and then he said, within a week, we have a seed grant deadline, KRSC grant at the time. So maybe write a proposal for that, and let's see what happens. So I wrote, a proposal for that seed grant. So we got it, and that's how this program started. So hopefully, okay. But let's just go back a bit. In the past, 100 years, we've relied on glass slides, and that's still the case. And for that reason, we have lots of archival material, like, in hospitals, and by law, we have to keep them. But, there has been significant growth in our ability to digitize histopathology slides. If you get one of these sort of next generation slide scanners, one is Leica 450 as an example. So it can basically scan 81 slides, I think in 1 hour. I'll have to look at my slide. Yes, in 1 hour at 40x magnification. So it's, and then each of these images, each slide, you would get somewhere between 2 to 5 gigabytes of data. So that's a number. So what does that mean? It means like that actually each of those is equivalent to sort of like 1 hour of movie. So the amount of information that is within those slides is actually huge. And imagine if you go back to the archival material and scan them, so you can have a lot of data, and you can have potentially you have basically follow-up data for those patients as well. That becomes a huge resource to do artificial, AI and machine learning on those slides, okay? So now the question is that how can we actually unlock transformative potential of AI to revolutionize patient care, and more specifically within the cancer research space? So at the time, again, 2019, we started this initiative called BC Translational Digital Pathology AI Initiative. That is a collaborative, basically group of more than 20 clinician scientists from different institutions in town. And it was basically driven by the healthcare team and us. And also, but we have valuable players from other basically health sites in BC, including, people from Process Center, BC Cancer, Providence Health, and, so many other operators. So the goal is to sort of like try to build what I call the plug and play AI engine that is in the middle, that you would get, let's say, the slides and potentially, down the road, like electronic medical records, radiology data, omics data, and then try to use AI and machine learning to identify, diagnostic markers, prognostic or predictive markers for cancer. And then we build it in a way that, if you have a new question for a given cancer, so it's modular enough that you don't actually need a lot of resources to start a new project. So that's what we call plug and play type of thing. It's not always like plug and play. It's not that easy. But my idea was that rather than trying to scale in terms of having 50 people that work on different aspects, you can probably scale with software and have 20 people doing the work of 50. That was the idea. But obviously today I'm going to mainly focus on ovarian cancer and also endometrial cancer studies that we're working on. So, so the question is, how can we actually benefit from AI in pathology? There are several ways that we can do that. One is actually improving clinical pathology efficiency by AI. That means, building better diagnostic models and algorithms, and imagine triaging cases that, so that the complicated ones or more sophisticated ones can be actually reviewed by pathologists. The rest, they can be actually signed off right away. So that is more about again, pathology efficiency. And also the other aspects that become, I think, more interesting as well is sort of trying to predict outcome of patients to specific therapies. And also, as an example, trying to identify molecular markers from histopathology images. So rather than, waiting, trying to set up different molecular tests within the healthcare system, which is very difficult and also needs, it costs money, hard turnaround time, all that sort of stuff. If we can actually identify some of these markers from histopathology images, that would be fantastic. Because these images, these slides, they get generated as part of the practice anyways. We just needed a scanner to scan and run the algorithm. So that was the idea. And then down the road, we were thinking, we haven't started this, but we're planning this, and I gradually accumulating data, is trying to combine pathology, omics, and radiology, because these data are being actually, or imaging modalities are being actually looked at in silos. So, and what I believe is that actually they have different complementary information they provide. And if we can build algorithms that they can actually basically ingest all the data, we can actually come up with better markers for therapeutic decision making. And the fourth one is more on the the first three are more translational work, translational research. The last one is more basic research that we're trying to basically link this data to sort of a spatial omics, and also linking to single cell genomics data that will hopefully derive some of the basic science work that we can, if we identify some hypothesis, take it to the lab and do experimental work. So I'm going to highlight a few studies, related to the first two directions. So the first one is just coming back to this pathology image synthesis. You may wonder, how these models actually work. Basically, these models are a class of these algorithms called generative adversarial networks, or GANs. The intuitive explanation would be that you have two AI models that are actually playing a game, and that game is, imagine one model is generating images, and then which we call it generator on the left, and also the other model is a discriminator that tries to tell whether that the image that was generated is actually real or synthetic. So this is again a competition between the two algorithms that hopefully because they provide feedback to each other. So this at some point they get good at it, meaning that the generator is going to get so well that the discriminator cannot actually tell the difference. And so that's how we actually generated those synthetic images. As a matter of fact, like people are doing the same thing, right? Like criminals, they can actually print money as well. So that's the same system that they try to print money. At some point, the police or whatever authorities they see okay, this is the feature that defines these fake money, and then they learn and they try to make it better. Okay, and so it's the same system, but not going into details of the models because that's out of the scope. But to just give you an idea, so it takes for one cancer, it takes about 1 week to train these models on really powerful machines. So, but once they get trained, then they can generate these images basically, even on your cell phone, you can actually use them. But training them, it takes a lot of resources. So this is just, a video that shows, how the model over time tries to come up with these images. It's about 1 minute, I think, but as it goes forward, tries to basically construct a pattern first in the context and then morphology afterwards. So for now, it doesn't mean anything, but so as you can see, there are some patterns that are emerging over time. Again, this is over a week that we've compressed it into a minute. Hopefully we'll stop at some point. But as you can see, so as it goes forward, it makes the images better. What we call these models are we are gradually actually increasing the capacity of the model. Otherwise, the model we cannot really train these models. So that's why we call it progressively growing the GAN model. But so we did this, as I mentioned in my first slide, we actually applied this to 5 different cancers and also 5 histotypes of ovarian cancer. We wanted to show that, we can do it like, 5 different cancers that you really have different morphologies. They look quite different. We can do that. And also, even if we do it in like, 5 histotypes of ovarian cancer that are closer, we can still do that. So that was, that's what we did. And then in order to test these models, so we basically put together a survey and 150 synthetic images, 150 real images, and then and we asked 9 board certified pathologists to look at them. The questions are actually within that questionnaire. So major one was, okay, so do you think it's a real or synthetic image? Can you diagnose this? Does it have enough diagnostic information? The 3 questions. So basically, out of the 9, also we had some pathology residents, 6 more pathology residents as well. But in any case, so they were not be able to actually tell the difference between these images. So In other words, like, it was like, mean accuracy was 54% and chance is basically 50%, just a little bit better than chance. And then these are actually expert pathologists, like gynae pathologists for the ovarian cancer part. So it's not like, let's say. So, and then similar thing in terms of diagnostic quality. So as you can see, like for the real images, diagnostic quality, they say 82% of those images have enough diagnostic information to diagnose those cases. With the synthetic images, it was 82%. Basically, pretty much, it wasn't possible to tell the difference between these images. And so one thing that the other experiment that we did is, like, this is the augmentation part. That what we did is that now we said, how can we use these models? Okay, we can use it for proficiency testing, for blah, blah, blah. But one thing is actually to augment AI models, because AI models actually need a lot of data. And then one way is to get a lot of data, which may not be possible for some cases, as an example of rare cancers. And then the idea was to see whether, we can actually use these images to train better models. So what we did is that we did 3 experiments. We used, let's say, some of these just real images. We trained a model, let's say 5,000 images as an example. Then we said, okay, we are going to add another set of images, like, let's say 5,000 more real images. And with the hope that, because the idea is that, again, these models, if they get more data, they will get better, okay? So if you add 5,000 real images, let's compare that with adding 5,000 synthetic images and see, how they perform. So looking at this one, just focusing on the ovarian cancer part. So this is what for the TCGA, the 5 different cancers. So this is the baseline, let's say 5,000 images. When you add 5,000 more real images, your performance goes up. That's what we expected because we have more data. But the interesting thing is that with the synthetic images, actually the performance also goes up. It is even better than the real images. So you may think why that is the case. That's up for discussion, but part of it is that because the images that get generated by the GANs are, I think, they're more pure, they have more morphological features and contextual patterns compared to real images. That's why they actually make the models better compared to real images. But anyways, just going forward with the applications, again, that was one application. As I said, we can use it for data sharing, proficiency testing, regulatory purposes. But what I want to highlight is that actually there's a downside and there's some challenges to these models. From the regulatory perspective, we really don't know, how these models are going to play a role. It's like ChatGPT. Okay? Nobody knows, how they're going to get regulated. So that's the same thing with these models and these images. And evaluation of these models are much more difficult because basically, we need pathologists. It's not like ChatGPT that everybody can understand at least the language. So it's much more difficult to evaluate these things. But the major, I think, problem that we are going to face, not just like in healthcare, in every I think industry, it's going to be what we call membership influence attacks and fraud. So usually people talk about AI for good, but the AI for not good is also going to happen a lot as we go down the road, because with these models, you can actually identify patients as well. And the one major problem that I see that's going to happen is that actually you can manipulate these images for, let's say for insurance purposes or to full AI diagnostic. But they're so real that you can't tell the difference. So if there is an attack to a hospital like IT and these algorithms, then you can basically manipulate the output of these systems. So I think AI security is going to become much more important as we go down the road. So anyway, I'm going to move on to ovarian cancer stock classification study. So there are five major ovarian cancer histotypes. General pathologists, the agreement between pathologists in diagnosing these cases is, I would say, low to moderate in terms of agreement, with kappa coefficient around 0.54, 0.67. Gyne pathologist experts, the agreement is pretty high, 0.89. So kappa of 0 means, basically no agreement. So for that reason, there has been, in the clinic, people rely on immunohistochemistry assays, and also, there's been some work on using like gene expression assays as well to make better diagnosis for the subtypes. So we asked this question, whether actually we can build a machine learning model that can actually do a good job in terms of diagnosing the 5 ovarian cancer histotypes. So first attempt, 2020. So we took 159 members. So we started in 2019. So it took a while to put together a data set. 159 patients, 5 histotypes, 309, the number of slides. We built a deep learning model that basically just high level, what we try to do is that we take like a whole slide image, we chop it into small pieces, and those small pieces, they go through the algorithm. So that, if we have like 159 patients, we're talking about maybe chopping it into 1,000 small, what we call patches or tiles. That becomes 159,000 examples. That's how you can actually, sort of like, address the problem with the number of cases. Because again, there is no way to train an AI model with 159 images. But this way, you can actually grow your data a bit so that, you can actually build these models. So anyway, so that goes through, anyways, training the model, so behind the scene, and then you get basically labels for each of these tiles, and then there are algorithms that you try to aggregate all the basically predictions for each of these tiles and get a slight level accuracy. So this is what we got at the time. So that was mean accuracy was 87.5%, kappa coefficient 0.81. That was really good. And AUC, area under care, 0.96. So I think that was a good start. But let's see what happened. So later on, we said, okay, so that was 159 patients. Now we're going to actually grow it. Now we have more data. Let's see, how the model works. And also, let's see how the model works when you actually try it on data from another center. So when we applied the same model to our own data, but this time 485 patients from Vancouver, and the mean accuracy actually went down to 65% and kappa 0.41. So we went down quite a bit. And the interesting thing is that on the external cohort, the accuracy went down to 20%. Again, chance here is 20% because you have 5 classes. That's why it's 20%, it's not 50%. So basically, it was just chance, and kappa was 0. Okay, so that was a bummer. So okay, so it's not working. And the reason is that, when you get the slides from different centers, or even like from the same center over time, they have different color profiles. Okay, it could be because of staining, tissue handling, all that, or even scanner. And that actually fools the AI model. So if you don't address that problem, so you're going to get to this issue of like basically you build a model that works on data from hospital A, but it doesn't work on hospital B. Okay? So then we refocused and said, okay, now we need to solve this problem. So the first attempt was basically trying to what we call normalize these images, meaning that try to unify the look and color spectrum of these images so that they are more similar. That's what we call color normalization. That's what we did. And what we got is that, so I'm just highlighting this area with, this is a baseline model without color normalization. When you do color normalization with our proposed approach, we actually got much, much better. And obviously the higher the better, that on the y-axis. That was the pairs, okay? And then we are now working on another strategy, which we call domain adaptation. Again, trying to imagine domain A could be Vancouver, domain B is like, let's say, Calgary. So we are trying to, again, come up with the algorithms that address this domain shift between the two domains, or it could be like multiple hospitals. So that was the idea with this study we call domain adaptation. So, but then coming back to our study, and that was done in 2021, I think, and then 2022, then we said, okay, now these are the number of slides that we have, number of patients we have, 485, the same pipeline as I showed. The only difference is that what we try to do, we still take the images, chop them into small pieces, and then do the color normalization. The rest is the same. So we did that, and then we said, okay, now we're going to apply that model to our held out set, which was from Calgary. So this is the external set, 60 patients from Calgary, and 60 slides, 1 slide per patient. And these are the results that we got, like just looking at this row. This is the mean accuracy. So we built 3 models. I'm not going to go into details of why we did that, but eventually what we got was 81.38 concordance, percent concordance with pathologist diagnosis. So which was actually pretty, I think, reasonable. And kappa value was 0.74-ish. And when we applied it on the external data set, which is again from Calgary, imagine that it was basically 20%. So we went up to close to 81% concordance, and kappa value 0.75. That was 0 in our previous attempt. And the aggregate model that we built, so which aggregates basically imagine like we built 3 different experts to diagnose, and then we try to aggregate those diagnoses so that it's more stable. And we almost got the same concordance, but our kappa value got a bit higher, 0.77%. Again, imagine rather than having 1 pathologist, we had like 3 AI pathologists that made the diagnosis. Then what we asked next was, okay, so it's reasonable. We said, okay, what if, like in practice, you don't look at just 1 slide to make a diagnosis? Okay, so you probably have a few slides or more that you look at and then make a diagnosis afterwards. So we asked this question of, okay, what if we add more slides and see what happens? And as a matter of fact, for some of these cases, we had more slides, either 2, 3, but usually like 2 or 3. It wasn't like 10 or 20. So our accuracy actually went up to 86.56% from 81%, and the kappa value went to 0.81%, okay, compared to 0.73. So this means that, okay, if we add more slides, AI model is actually doing a good job and actually corrects some of the errors that it could make. Next, what we did is that just on the external set, so in total, we had 60 cases. Out of these 60 cases, 52 were diagnosed correctly by the AI model, meaning that 8 cases were misdiagnosed. We said, okay, now let's see what happens if gynepathologists actually review these cases. Let's see what they say. Is this something that we can actually incorporate in the AI model? So 2 gynepathologists, Blake and Navina, actually both reviewed these slides, and 8 slides. They were blinded to the AI diagnosis and also to the original diagnosis. So they were asked, okay, you have these slides to make a diagnosis. The interesting thing is that when we did that, we realized, okay, so out of those 8 cases, I'm highlighting the ones in red. So AI prediction was, let's say, high-grade serous ovarian carcinoma, and actually both of them said it is actually a GSC. But the reference diagnosis was endometrioid carcinoma. Okay. So meaning that, so just highlighting those 4 that are in red, our diagnosis or predictions actually agreed with the two gynecologists in 4 of the 8 cases. So what that means is that actually we are doing much better than 81% if you just take the gynecologist diagnosis, because it was just based on one slide. Imagine if you have more slides, that can change. But with one slide, so we had concordance in 56 out of 60 cases with gynecologists, which is really good. That is about like 93% accuracy in concordance with pathologists. So just the time, where are we going from here? So we are trying to validate these models on larger cohorts. One is from a consortium, more than 5,000 cases, so called Auto Consortium. So that is being done as we speak. We are also building models so that we try to detect outliers, meaning that if you have a case that is, let's say, ovarian cancer, suspect of having ovarian cancer, if you want to build AI models, it could be like, okay, so I know it's one of the 5 histotypes, but I want the histotype, but it could be like, okay, so just one case that comes in, may not be any of those 5. So what we are trying to do is build the models that would say, okay, so this is not any of those 5, maybe it's one of the rare subtypes of ovarian cancer, then it goes to the histotype classifier afterwards. So that's the outlier detection. So we are actually trying to launch an AI grant challenge on some of these data. So hopefully later this year that will come out. So this is the largest, I think, AI challenge on ovarian cancer in histopathology. So it is hosted by Google. So hopefully now we're working on the agreements with BC Cancer and also Google to make that happen. And also what we are doing is trying to characterize rare cancers, meaning that, as I said, a lot of these models, they need a lot of data. How can you actually build models that work off of let's say 5 or 10 samples? So there are some strategies that, fortunately we can use to do that. So there are some work in that area. The other interesting work that we're trying to do is basically what we call cell identification, which I will highlight in the next slide. And also linking to molecular data as well. Just quickly, just showing this because this is sort of important as well. Imagine you have histopathology slides. What we are trying to build is models that would identify the cells, not just identify them, but label the cells in an unsupervised way without human intervention. And then from these images, that once we identify those cells, we are trying to build graphs. Basically, we are trying to model the interaction between the cells. And then from those interactions, we are trying to actually see if those interactions somehow correlate with outcome or response to therapies. So this is a highly interesting area that we're working on. And imagine if we can apply to archival data without any annotations, that would be fantastic. Otherwise, you can't really get pathologists to annotate each cell, and imagine you need 20,000 of those cells to build these models. So that's an interesting area that we're working on, and I think it will have a lot of potential going down the road. So I think in terms of time, I have maybe 5 minutes. This one, I will try to quickly go over this because this is also an important study that we're working on. This is on endometrial cancers. So the Cancer Genome Atlas project in 2013 came up with 4 molecular subtypes of endometrial cancers. And then Jessica McAlpine and basically colleagues, everybody from Wolfcare, actually came up with this classifier called PROMISE that basically tries to came up with an assay that is more clinically applicable, that sort of mimics those four molecular subtypes. Because again, the TCGA discovery was done on fresh frozen samples. It wasn't possible to take that. So that was the idea. And then these 4 subtypes, again, so some of you are familiar with that. poly mutant cases, MMRD, P50 abnormal cases, and also NSMP. This is no specific molecular profile, NSMP. That is actually defined by exclusion, meaning that if it doesn't fit within one of those three categories, poly, MMRD, or P50 abnormal, then it's going to be NSMP. So the problem is that represents about 50% of cases. And the outcome, this is a specific survival, I think. Yes. So the outcome is sort of like, it's not homogeneous. So some patients, in other words, are doing well, some not doing well. So the idea was, can we actually use AI to identify some of the bad players? So we built an AI classifier that sits basically over here, tries to differentiate between the NSMP cases and P50 abnormal cases. Okay? And so I'm going to skip the design of the model, but when we built this model, so we had two data sets, one from Vancouver, the other one from Germany, and also TCGA cohort as well. So the accuracy of the model, just focusing on this last column, was 83% in our discovery set and 80% in our validation or held out set. You would think, okay, 80% is not bad, but it's not like 95%, But that wasn't really the purpose to get to 95% or 100% accuracy. The purpose was to see whether we can identify, because we know that these AI models actually are doing a good job. We wanted to see whether the AI model identifies some of these NSMP cases that look more similar to P50 abnormal from the morphological perspective. That was the idea. So meaning that 20% is actually not a bad thing, and we'll see why that is the case. So basically, then imagine, so you get an AI classifier that takes NSMP cases. It tells you whether it's NSMP, 80% of cases roughly. And 20% of those, it says that it's not NSMP. It looks more similar to P50 abnormal. So we said, okay, maybe then the outcome is going to be as bad as P50 abnormal cases because they look more similar to P50 abnormal cases. And as a matter of fact, I think we got lucky in this case. So those patients, what we call P50 abnormal like NSMPs, they actually do worse compared to the rest of the NSMP cases. And this was validated in our held out set, both PF progression-free survival, disease-specific survival, and also the overall survival as well. So then we looked a bit into this and realized that there are some of the cases that we identified that were bad actors. They were actually P53 mutant cases, because all the P50 abnormal cases are basically identified by immunohistochemistry. So then they're not really P50, they're not really NSMP because they have P53 mutations. So we remove those ones and say, okay, we ask the same question, does it still hold? And okay, we got lucky, I guess. We see that still, when you remove all the P53 mutant cases, we still see that signature that P50 abnormal like NSMPs, they do worse compared to the rest of the patients. And we did a bit more work into this. We took some of these cases. We did shallow whole genome sequencing and realized that these cases actually, the bad players, they have more copy number, basically copy number burden. And in other words, unstable genomes compared to the rest of the NSMP cases. What I'm showing here is this is the copy number basically burden for NSMP cases. These are the ones that we found that they have elevated copy number burden. And these are the P53 abnormal cases. So it's somewhere in between. It's not quite there yet, but it's somewhere in between. So the other question that we asked was, okay, so maybe then what is happening is that these cases or NSMP, at some point maybe they acquire some of the P50 abnormal phenotype as they go forward and some of the variations. So we looked at gene expression profiles for these cases. The interesting thing is that that story, I don't think it holds true. We still need to investigate it further, meaning that I was hoping that, these or the other way is also okay, that these cases, they acquire some mutations, and at some point they acquire, P53 mutations as well. But when you look at the pathways, there is zero overlap between the pathways that are activated in this cohort versus this cohort, meaning that the etiology is probably different. Eventually, they come to look similar, but that doesn't mean that they actually arise from the same origin. But obviously, that is a hypothesis that we somehow need to investigate, but we'll see what happens. But anyway, so where are we going with this? I'll try to wrap up. I know it was a long talk. So we're trying to validate this in a larger cohort from across Canada as part of the TFRI initiative that we have. And also what I didn't talk about is that we found some NSMP-like P50 abnormal cases that they do actually better, like these ones. And that we still need to investigate those and see if the combination with other molecular markers and genomic data will improve this stratification, meaning that we might be able to identify some good players within the P50 abnormal cases, because they usually do really bad compared to the rest of the patients. And obviously trying to see, build the infrastructure to be able to apply these to biopsy material. Anyway, so I'll try to wrap up in 3 minutes. And hopefully what I've shown is that I've shown the potential of AI that can actually, we can help patients. Okay. And then one way to do that would be like, imagine like if you have a cloud-based system that, every hospital, doesn't matter where they are, geographically, they can actually just scan or send the slides to somebody to scan, upload it to a cloud system that gives you a diagnosis or a predictive or prognostic marker. So I think the barrier to entry to get these tests will be much, much lower than like genomic tests that they imagine like, VGH or BC cancer can actually implement with the other places they can. So that's what we're hoping. So I think the potential is really high, but also, there is a lot of question about, AI is going to eliminate jobs. What's going to happen? And I think most of it, again, has been around eliminating jobs, but I think we need to look at a positive aspect. And, and people may say, okay, what is the, risk of widespread AI in pathology, specifically more on the diagnostic side? I think the predictive tests, they still have value, that whether you do genomics or AI, that's not going to replace pathologists. But people may think, okay, so you be a really good diagnostic models, it will replace pathologists. But I don't think that's going to be the case. So, and, it could be like, automation bias. If my kids use spell check, they will never learn to spell. Maybe that is true, but, I think it's okay. So aging population, lack of pathologists makes, us to think about ways to basically make the pathology diagnostic process more efficient. So I think this is where that AI can actually help, because the number of trainees in pathology residency programs is going down. We have much more older people that they will need care. This is the way to maybe like, compensate for that. And, can past experience help us to predict what's going to happen? I've included a few examples, like industrial automation as an example. Yes, it actually transformed workforce. And did industrial farming eliminate some forms of farming? Absolutely. But actually, it also amplified our ability to produce more food. So again, so there's a downside and upside. Same thing with AI. So ATM machines. So this is actually came out in New York Times last week. ATM machines, I didn't know about it. Obviously automated, process of like dispensing and depositing cash and that sort of stuff. But did actually the number of bank tellers went up or down? It actually went up. Why do you think that was the case? Any guess? No? More, yes. I mean, opening branches, I would say at the time, like even the ATMs were not there, it was very expensive and you needed a lot of people, okay? And then imagine ATMs automated that process, that they didn't actually need tellers to help with, cash stuff. It was more about like building relationships. It was much, much cheaper to build, basically start new branches. You have an ATM and a bunch of people that actually build relationships for banks. That's why actually the number went up. I really didn't know about that, but that was the case. Same thing with ChatGPT. This is a study that from OpenAI, they built ChatGPT. They're saying that 80% of jobs, in 80% of jobs, about 10% will be sort of like, could be automated with these models. Yes, that is true. But there's a Fortune 500 company that is actually using ChatGPT to increase the efficiency. And then with that, they've improved their efficiency by 14%, especially for the, employees that they're not doing well. By suggesting basically things that, they're in the call center, how to respond to questions and that sort of stuff. So that increased the efficiency much more. Again, so I think we need to look at the positive aspects rather than just, the negative aspects. And I think down the road, we will see like, these models as diagnostic adjuncts to pathologists rather than the other way. With that said, I'm going to skip this part. This is interesting, but I'll skip it because we're out of time. But the last part is obviously acknowledgements that, the whole work has been, I think it's been possible with, I think, the great collaborators and mentors within, OFCARE, Gynecologic Cancer Initiative, and also in town that have made this work really possible. Otherwise, with the, we can't really do anything. And we've been lucky that we're actually integrated within the healthcare system that we can do these things. If you're isolated, you can't really do that. You can't really identify interesting clinical questions. I think that is very important. And also, obviously, my team members that they actually did the job. So, and I may be taking more credit than them, but the real credit needs to go to them that they made it happen. Thank you, and happy to answer questions.